that we're going to come, right?
I guess.
Ranging is not in the morning. Probably the people who have no excuse to be late are the ones that are late because the office is just upstairs.
Oh, there's no one there.
Oh, nobody else is there.
It's always the hardcore end up with.
It is. Well, that's all right. Yeah, we'll go for the hardcore. So yesterday we had a complete schedule. Today we have no schedule. So the thing is, yeah, we're here. We're going to try to provide some information that might be of interest or use. We want to hear from you guys on what you're doing, and yeah, just kind of use the day as productively as possible. So talk about SIMPEG and Python programming, and some tutorials on Inversion, whatever. So it really just depends on what everybody's interest was. And can you just tell me your name again, sorry, and we'll just go around, and then what you're working on.
I'm Shohei. I'm working with Silent.
Okay. And any connections at all with EM?
I'm not really sure for this moment because I'm working in physics of elastic scattering to structure medium, so I'm more interested in fundamental EM.
Yeah. Oh, yeah. I thought because I was sitting in the back. Okay, and Ruben?
Yeah, so actually some similar to the scattering, we're looking at the ability to use the scattered wave to monitor subtle changes in the rock matrix or cement.
In the lab, or?
Well, with the objective of precursory identification of material yielding and then failing. So as a alarm system monitoring method, but I'm doing it currently in the lab and then numerical modeling. So I would be interested to see if electromagnetics can be used also as a subtle detector to small scale changes in scattering properties. But it's maybe a bit of a stretch for the day, so we should focus on the people who are.
Well, it's an interesting problem. I'm not exactly sure where the state of the art is with respect to using.
Because I'm looking at things currently on the grain scale interaction, so the link between seismic scattering properties and the very subtle onset of material failure. So when the first microfractures form, but the only link I could think of was seismoelectrics, maybe. Yeah. There was a PhD in Niels who was working on that here, but not in terms of monitoring medium time-lapse sets.
But I thought with seismoelectric, you actually had to have like a sharp pulse that was going, so something would have to.
So what I'm doing is active. It's all active monitoring. So I have a constant source monitoring the changes in the medium over time towards failure. Also, with Shell, we're doing work on monitoring the subtle pressure depletion curve. So you deplete a reservoir, and you monitor the scattering properties of the medium throughout the depletion cycle. And we can currently replicate the pressure curve from just the coda of the wave. You can get a description of the pressure curve without measuring pressure, just because of that.
Oh.
So there's some of that.
Yeah, my name is Jaap Mond, and I'm just giving courses in geophysics, but it's seismic mainly, but also non-seismic methods. I have no applications in mind at the moment, but I would like to know about what you could apply EM for. And I think the course is going to be successful if at the end of the course, I'm no longer afraid of EM.
Oh, I hope we made roads there yesterday.
Yeah. So, Chef, yeah. And I'm working as a geophysicist for monitoring on the one hand, so reservoirs, so it's oil, gas, but also CO2. I did a lot of work in the past years, passive and active. But so the electromagnetic monitoring of deeper reservoirs, but also for groundwater applications. And for that, I have thought of something, and I wanted to discuss it. And I have a nice, maybe you are looking for case history. I have a nice case history of a combined application of vertical electrical sounding and time delay in the Netherlands. To show that as well.
Yeah, that's perfect.
And well, I have also a story about monitoring oil reservoirs with a specific configuration.
Oh,
Anyway, let's see when we
that's
start
perfect.
with the idea and then the cases.
That sounds perfect.
Okay.
I only joined last week, so I didn't work much up to now, and my topic is imaging and detection of induced earthquakes that are really small. So, yeah, not sure how to apply again.
So induced earthquakes, like from fracking or from injection of various
Yes.
kinds of fluids? Or?
Mostly from the Delineating area would be, or
I'm sorry?
from the area in the north part of
Groningen gas field,
the gas
Oh,
field.
the largest gas field in Europe. So
Yeah. There's some induced earthquakes.
they've got big problems with subsidence and houses cracking and smalls.
I see. So induced just caused by
Depletion.
extraction as
Yeah.
opposed to
Over-
injection.
Yeah, from over depletion of the reservoir, it's beginning to, it's a big issue for Shell. And the Netherlands.
Well, there's issues of substance. We'll be going to Mexico City in about a
Yeah.
month or so, right? And
Yeah,
there
I'll
they've
see.
just been withdrawing water. And if you see pictures of Mexico City, you look down the street, it just looks like waves.
My name is Ferry. I work for a consultancy firm and I've been using mainly GPR and magnetometry for the last 12, 15 years. But the last few years I've been using the new generation of the EM31, EM38 for archaeology and geology. But it's fairly new for me. Also inversion and making 3D geomodels. It's a relatively new topic for me. That's the reason why I'm here. And I don't know if anyone has any experience with the CND explorers, multi-depth EM sensors.
No CM.
CND explorers, they call it. Mini explorer, the explorer. It's a multi-depth EM sensor. I've been using it for some time now. It works very well. It's used
That's a time domain system, is it, or frequency? Time domain system or frequency?
frequency.
Low induction also, right?
Also, yeah.
Low induction.
Yeah.
Geonics type of thing, but
Yeah. The newer version of
new generation.
new generation, yes. So that's my reason to be here.
Yeah.
As at the outset, to overcome my fear of EMs, apart from GPR.
Fear. Yeah, back up.
Yeah, so my name is Jan Willem. I'm also a PhD in the group here. My topic is about marine seismic, and especially the effect when you have a sea that is not so calm. So when they do at some point they stop doing measurements, but at some point they still do measurements, and there's influence from the rock sea when you get that effect. And well, I don't have much experience with EM, because last summer I went to a field camp in Russia, and I was mainly involved in the seismic part, but there were also people doing EM. So I got a bit interested in it, also because they couldn't, there was kind of a language barrier. So when I asked questions, I didn't really give me clear answers how it worked. So that's why I was a bit interested in it.
So what sort of EM were they doing?
Well, they did. Because yesterday we had the course about fundamentals. So I asked them to give me some presentations, and we did the risk, TC resist. Yeah.
Okay.
I think we also did another where we had with
EM31.
yeah, I think so.
Okay, and
so my name is Chris. I'm also a PhD here in Delft, and my topic is on Marchenko imaging. So that is about correctly describing the multiply scattered waves in recording, seismic, or I think could also be GPR in theory. And most people do it for acoustic waves here. I do it to extend it to elastic waves. Don't see a direct application of the EM, but I know that Yuri had this idea yesterday, like as a starting point to do Marchenko imaging, we always need a smooth velocity model of the subsurface. So Yuri mentioned maybe EM could help to get a better smooth velocity model. And further, there is another PhD, Binkum. He's working on Marchenko imaging for EM waves. So I don't know, I just met him once, but he's using electromagnetic fields and tries to apply Marchenko imaging to that. So he's working with David, so maybe David has more insights into that.
Yeah.
Maybe so.
But this other person, he's not here, or?
No, I don't know if he's not in Delft these days, or just because he's one of the few PhDs not the PhD on for some other office. So
Wow.
you have the name?
In the basement or something.
No, I'm the latest sitting next to Binkum.
He's not the main person.
No, it's Case Wagner, and it's not the both workmen.
Okay.
And David is the one who also wanted to electromagnetic.
Fascinating topic.
Yeah, I guess in principle, because it's using the wave equation, should be applicable in some way, but I also don't know how much internal multiples are an issue in EM data processing.
How multiples an issue?
Trying to, and there's been a lot of work, especially a couple of decades ago, where people took the EM equations and you could write them because you've got reflection coefficients, right, and transmission coefficients, so you can write things in that manner. You can actually solve problems in that manner. But when you actually try to work through that kind of analysis, you just get kind of trapped up with the fact that these EM waves basically only go in a fraction of a wavelength, right? Because by the time you get down to one wavelength, you're basically e to the minus 2 pi in amplitude. So it's a bit of a different beast. Mathematically, you can write it in that form. We actually formulated the magnetotelluric inverse, the 1D MT inverse problem, in terms of finding reflection boundaries and ending up with something actually that looked like a seismic profile. But I haven't seen, I really haven't seen applications where this stuff works in practical cases. The mathematics works. There's been a guy named Stanoff did some reverse time migration of electromagnetic data. And on paper, mathematically, it looks great. Looks like it's fine, right? So that's where, you take the seismic equations, you take the EM equations, you can make correspondences. Every term comes up. But in reality, because the attenuation is so large and the traveling wave component is so small in EM, there's all kinds of practical difficulties. The EM migration could only work if you had a very large number of receivers, and if you knew basically the conductivity model exactly, which is what you're trying to get. So it's kind of like working in seismic and not having a good velocity model and trying to migrate the data.
Because I remember people looked at even at the core mental boundary with MT data, with long wavelength, and I could imagine that given the different discontinuities you have in the crust and so on, that you might have multiples also bothering you.
Yes, but the multiples all kind of get concatenated in with your final wave field. So if you solve the MT equation exactly, you actually are handling all of the multiples. So everything is in there. But if you try to recast it in terms of up and down going plane waves and trying to keep track of everything, it becomes very difficult, very unstable, and hard to get very much out of it. But if you just simply take the equations as they stand and forget about anything that is up going, down going, and just solve those equations to get a conductivity, then you're actually on pretty good ground. People can do that. And the forward problem actually for some simple problems like the 1D MT can still be solved in terms of propagator matrices. So keep all your reflection transmission coefficients. But the inverse problem is then sort of formulated so that you're really looking for like a change in conductivity. Just change the value of conductivity of each particular layer and then go ahead and solve the forward problem. You're doing that with recursion, but you're never actually formulating the inverse problem in such a way that you're trying to find reflections from primary and multiple events.
So is the inverse problem even more opposed than, say, in the case of seismic?
I think these problems are probably equally ill-posed. I mean, there's a question of resolution, but if you accept that you're just going to get poor resolution out, I think the problems are essentially the same. You've got some function that you're trying to find, you're going to discretize it, you've got some way of solving forward simulation, either through, say, finite element, or finite volume, or finite difference, and the procedure that most people use, at least in the non-seismic methods, are just kind of a Gauss-Newton procedure where you've got a number of parameters and just go ahead and try to solve it. The problem is doing that in seismic is you just got such a huge problem that are hard to work with. So actually, did you sign the book? Had you signed this book? No. Can you just focus your name and email? I also need to know what you're working on. I thought so. So this is kind of an interesting audience because usually we've got a lot of people here who have somehow been, really intimately connected with EM and have been challenged by some particular aspect with interpretation or trying to figure out what they're doing or trying to extend something. In this case, we've got quite a few people who are basically in seismic and trying to look for some kind of connection. So we have, from the point of view of EM, there's yours, which is got multiple receivers, I guess. Whatever, CMD was it?
CMD, it's called. This is by Czech manufacturer GF Instruments. It's especially in the field of archaeology, it's getting very well known.
Okay. So we have a lot of material that we could have covered to kind of round out the course material that we presented yesterday, but I think a lot of it's not particularly of interest. The only connection that, or at least the one connection I can find from material that we actually have, is the induced polarization for landfills. So that's at least one tangible connection with one person, and it's also maybe something that is of interest to other people. And the GPR. No.
Right, I thought the consensus yesterday was people were.
Yeah.
Well, I wouldn't mind to learn a bit about GPR. If we have time.
Yeah.
I'd like to hear.
Okay. Oh, then that's good.
Yeah.
Good.
We were just discussing yesterday, I thought because it's similar to
Yeah.
processing, that's that people were.
Well, actually that actually might be good. Who is familiar with GPR?
Processing ones.
That's all familiar.
Yeah.
Okay.
Pushed it around a bit.
To finalize the processing.
No, pushed it around. Found some old.
Very different from.
Oh, and what did you find?
Well, it was an old monastery on the border between those Germany and Switzerland, right on the river, in the middle of the river, in fact. And did we find anything?
We found some old walls.
Old walls, yeah.
Church which were redundant there.
I found the pipe going from the monastery to the toilet. I remember that. Yeah. But yeah, we've used GPR.
Oh, finding a pipe from the monastery to the toilet. Achievement. We're definitely worthy of a case history.
Yeah.
Well, unexploded ordnance side.
Archaeology, you show utilities,
So you have,
everything that's fairly shallow.
and then you should you also might use a lot of GPR on it, right? So you also use GPR on it.
Yes, yes.
What, for unexploded ordnance?
If magnetometry isn't working because of background noise, then we use GPR. But it's much more difficult for you, so much more difficult than using magnetometry. So if I can avoid it, using GPR for you, so I will.
I think in North America, the methods of choice are, magnetics is kind of, it provides some information about potential items, but it picks up everything, and it's very hard to do any kind of discrimination. So in order to do discrimination, you need to use some kind of frequency or time domain systems. Most of them are time domain systems, and they've now evolved. Actually, it's really quite amazing for the last 5 years of how they have evolved. We're associated with a group called Black Tusk. In fact, most of the people there kind of came through UBC and started their own company. About 3 or 4 weeks ago, at least in the Vancouver paper, there was a big flashy picture of the Queen Elizabeth aircraft carrier going into Portsmouth in England. And they showed this aircraft carrier going in, and it was a big deal for them because previously the channel to go in was not big enough to have this size of boat. So the last couple of years, they've been spending kind of making the channel wider. The difficulty there was that there was a lot of unexploded ordnance. Okay, so what they then did is they built this machine that has got 5
Implements on the board.
Anyway, there's sort of 5 of these built on. And each of these has got 3 components, magnetic field sensors. So there's sort of 5 transmitters, and I think I think it's, let's see, trying to remember. I think it's close to 20 receivers, 3 component. So it's like 60 receivers altogether. So you got 5 components and multi-receivers, and the idea is that you're exciting this object, from many different directions, at one particular time. So you've got all kinds of critics. You're cycling through these transmitters, measuring the components of the 3 components of the magnetic field in a time domain sense, and then you're inverting to try to find a decaying dipole. So if you have an object that is small like this, then it'll have a time decay curve, which is can be parameterized, in terms of a number of parameters. So this is just a kind of a parametric way of representing that decay, the dipole. And for an object that has got a bit of geometry to it, it can actually have 3 independent dipoles that are decaying. So that means instead of solving the full 3D electromagnetic, time domain electromagnetic problem where you're dividing things into whole cells, you just have a parametric representation so that at each point you're representing what the fields are like with 3 independent decaying dipoles, each of which have got a number of parameters. So you end up with having to find, 15 or something parameters, but then you're exciting the object from many different directions. So and then the way you then use this is you find these values, and then you've got libraries to kind of look up and see how things match, and you can actually discriminate as to what object this is. Okay, so that's sort of the procedure. Hardly anybody's using GPR, so it's magnetics and time domain EM. The thing that was interesting in the Portsmouth example is they designed the system to go onto a ship so that it's moving along at a fairly low rate. The data are being acquired, and in real time, the data are coming back, they're being processed, they're doing the inversion, they're doing the discrimination, and then if they find that there is an object there that needs to be remediated, then right behind this boat, there's sort of another boat, but it's got kind of a big vacuum cleaner on it, right? So it's blowing stuff around and sort of making this item so that it's quite clear to be extracted. And then you've got something coming along with a grappling hook, hangs onto this guy, pulls him out, and then they pull it out to sea and they explode it. So they found, I think, 5 or 6 of these 500-pound bombs this way, and then with that, they were able to, then safely go ahead and excavate the rest. But I thought it was kind of it's just kind of like a neat example because it shows, first of all, that you need to, that you can find metallic. So these are conductive magnetic objects, right? So you need to worry about the magnetic permeability, and it shows that. Just those principles of exciting in many different directions and measuring many different fields, that you can actually get pretty reliable estimates of what's there. Yeah, so it's kind of a nice use of geophysics, and it's good to see that. Well, maybe then the 2 things that we could do this morning that might be useful. I could talk just a little bit about material that we had for landfills. We could just discuss the IP, and then we'll do a quick run through on the GPR, and then that's probably good. And then we'll turn it over and hear from you. Does that sound good?
Just so you know, Doug, we have to stop at 12.
Okay.
For the reason that this room was booked for 1 hour. Probably people won't show up. It was booked like 4 or 5 months ago for 1 hour in the day. I had to book around it. But let's say we just planned at possibly someone will do something here now. I don't know. Probably not. Probably they forgot about it. Yeah.
You can't contact you?
I wrote to the secretary to confirm the booking, see who it is, but she hasn't responded. Yeah. It's just because the start of semester, I think people book rooms just in case, and then they don't show up.
Well, I think that that time is doable.
It's lunchtime.
We have, I mean, this is going to take an hour at most, probably less.
It makes sense anyway that we go to lunch maybe a little bit earlier.
Yeah.
Because heaps of people turn up there.
Yeah, no, I think
We have a cafeteria at the top.
we're in good shape. So a problem that is becoming,
I was just wondering about whatever.
so a problem that's becoming more pervasive in North America, I think is typified by what's happening in Tucson, Arizona. Has anybody been to places like Tucson? Southern desert, nice place. All the Canadians, well, not but a lot of Canadians come to places like this because you know the winters are pretty brutal, right? So going to some place that's nice and warm.
All hugging on the border, right?
Yeah. So I think in 1953, this blue area in here, that was the size of Tucson, the city of Tucson. And so if you're a city, you've got to dump your garbage, right? So you find places out here, dump them. They're a long ways away, right? But then gradually, you know, the city kind of builds up, and right now, here's the current sort of outside boundary of the city, and you can see that it encompasses a number of these landfills. So they create, you know, health hazard. They're water contamination. Water contamination is a big thing. Construction hazard, but one of the biggest things is that it devalues your property value. So if you've got if you own that property and there's part of a landfill on, you have a very hard time unloading it. So that means they need to go in, find these places, characterize the size, waste, and kind of monitor the reclamation. So this is the sort of the type of stuff that they could have. You could have kind of electronic technological stuff with lots of metals, construction debris, wood, cement, earth materials, various kinds of clays, and green waste. The techniques that are generally used are electrical resistivity, but you can see that they're not completely uniform. Certainly anything that's metallic has got a very low resistivity. Construction debris might be high. Earth materials, a lot of them can have a low resistivity. Green waste is very low. Magnetic susceptibility is a little bit all over the map. Some of, you know, if you've got, you know, scraps of iron or something like that, so if you're burying that kind of stuff, which could be construction debris from rebar or metallic, then magnetics is good. Earth materials and other stuff, it's not necessarily. But the one thing that has come up over the last couple of decades is that most of these materials could be chargeable, either significantly or weakly. So
that is all relative to the country rock.
Yes, yeah. So here's, you know, because of that physical property table, this is what is generally done. So a magnetic survey, so he's got a magnetometer on here, just kind of walk over. DC resistivity for electrical conductivity, or so here's three things. You could use DC resistivity, that's been pretty popular. Here's your EM31, So the EM31 is only a single frequency system, so it's about 10,000 hertz. So it doesn't provide you with a large amount of information, but it's a good mapping tool. And then this is a time domain instrument here with a coil transmitter and a receiver.
What is that? Time domain?
61.
Yeah, this is the EM61.
EM61. Geonics.
Yes, geonics, yeah. So these slides were actually taken from a leading edge paper by Zong Geophysics. And the only purpose for them is just to kind of show what the images are like. We talked yesterday about pseudosections and going from pseudosections back to recovered resistivities. Here's the resistivity that was, so you do a DC resistivity experiment, here's the resistivity, and you've got red in this case is really low resistivities, and green is higher. So the outlines of the pit from the waste boundaries on a historical basis is given like this. So a little bit all over the map. Chargeability, however, if you look at that, is given by this. So here's the chargeability section.
How come resistivity is so much deeper than the chargeability?
Sorry?
Well, the brown of the resistivity is much deeper than the chargeability. How can that be? In depth.
Yeah, so here's your elevation, right? So those are the same. Or you're just saying that this top
Chargeability
region
is rather shallow. And
yeah.
The resistivity looks much deeper. It's on the after inversion, I reckon.
Yeah.
Yeah.
Yeah. So the point is here is that there's chargeable material up here, but it might not necessarily have a really low resistivity. So there's not a one-to-one correspondence.
Okay, so the brown from resistivity is coming from other sources than, say, the...
Yeah, I have no idea what any of this is. The only thing that's known here's the limits of the waste dump, and here's what you get up in resistivity, and here is the IP. So, yeah, so the fact that the IP is kind of in here and actually coming up close to the surface is perhaps good. Similarly, if we look at another, so that was one that had mixed solid waste, and this one's got construction debris. And in this case here, we've got sort of, some kind of low resistivity. Here's the outlines of the pits, and here's the IP section. So again, that's your kind of correspondence. When they were, they actually collected data over many different lines. They inverted each of these data sets, and then they looked at the final chargeability and kind of ended up with 4 regions like this. They wanted to do test drilling to see if that was, if those are correct, but they didn't want to actually drill on any place that had chargeable material or that they thought was waste, because they were worried that it might, just by putting a drill hole through, that it might contaminate things. So they just thought it was kind of interesting. They took these images and drilled right beside and were hoping not to see anything, and they didn't see anything. So there's chargeable material, but it's not here. It's like the first time I read that, I thought, like, okay, what's that?
Seems like a hard thing to sell to someone.
Yeah.
Yeah, we drilled exactly where we thought it was, and it wasn't there.
Yeah, that's a good job. I'll pay you double. So here's another example. Actually, this one, this type of example we see in a number of places. So basically what you probably had was like a flat area here, maybe a hill, and then they just kind of keep dumping stuff in as time goes on, and you end up with final topography that looks like this. So The color scale is resistivity. So the red is low resistivity. So you can see there's low resistivities here, and there's low resistivities out here. The contour levels are the chargeability, and you can see that that is kind of coinciding with this region here. You can see smaller stuff out here. So the point about this is that the historical boundaries of the waste stuff are nicely kind of delineated by the chargeable material, and all of this low resistivity up here is not chargeable, and that is very likely the leachate. So what happens, you get stuff that's here, water goes through, takes out of that a lot of metals and brings it down here. And this is the stuff that people are really worried about, right? Because that's going potentially into the water supply. And then with the case with organic waste, resistivity kind of showed that up, but it still had a bit of a chargeability signature, which is kind of interesting. Why are leaves and organic waste? But
so I'm asking, it's not the pore fluid that causes then the IP, but it needs to be the material in which the pore fluid is that causes the
road
IP.
restrictions. So you can have this.
Yeah.
Right. I mean, it's a combination of the fluids and the existence.
But the contaminated fluid wouldn't cause by itself IP.
Right. That's great.
Okay.
What's interesting with the chargeability, it's such a defined cutoff compared to obviously resistivity. It's really is or isn't versus higher or lower resistivity.
And that's really the kind of the take home. Yeah. The take-home point here. Here's one that this is probably kind of like an iconic example. This is what people were looking for, right? So the waste stuff was over here. Don't have that one, and so it's low resistivity and chargeable. They coincide.
Yeah.
So, and here's somebody was mentioning about having to do also maybe do monitoring. Was that you for the landfill? Yeah, so here was an example with municipal waste. There was a 2003 survey. This is the IP that was obtained there when they first started to reclaim the area. So that was the initial IP, and then they did a 4-year bioremediation program. So I'm not sure. They had air sparging and different kinds of things that they were trying to clean the place up. And I think it was 2009, so 2 years after the remediation, you ended up with a chargeability section that looked like that. So that was kind of nice. So from the point of view of monitoring, perhaps even a surface IP experiment done with time can help you sort of see how well you're doing with.
What would have been the reason that it's less chargeable than after the treatment?
Well, I mean, that means whatever treatment they're doing is good, right? So I think they were maybe flushing stuff out, and so you're gradually getting rid of
The concentration of dissolved
So you remove small things. So the solids stay the same. That's the point.
Yes.
And IP associated with the solids somehow.
Yeah, it's associated with the matrix.
It stay the same in a biodegradation program. So it's interesting.
Yeah, I don't know exactly what the details are, but when they're going in and they've got they find a place that's contaminated, then they're doing something to try to get rid of that contamination. So somehow the IP is reflective of how much contamination that there's there, and this example showed that the remediation program, they felt if it was just left to its own devices, I think they thought it would be like 30 years or something like that to really clean up all by itself. But by going in and actively remediating and they felt they were cleaning the place up, and then they went and they did the IP, and it looked like that. So there's some kind of...
Or did they, by the remediation, stabilize the leaching process? Because like you said, the material, the matrix is still the same. You can't leach a brick or rebar in a few years to nothing. So is it the leaching process that stabilized?
I don't know. I somehow expect it's a lot of more stuff that's happening at a real microscopic level that is going on, but I really don't know.
Or does it mean IP is a combination of solid material and pore fluid? And if you then remove the pore fluid, maybe you have less IP. Is that the?
Well, I think so. I think it definitely is. That connection between the matrix, okay, and the fluids. But I think that raises some interesting questions that we could follow up on.
Yeah, because ions in the water, they don't give rise to IP.
No, you need to. So here's where, if you have clay minerals or something like that, then you've got that electrical double layer that's on the sides of the clay, and then if you've got ions in the fluid that can interact with that double layer, then you'll get an IP effect. So I think it's actually probably fairly complicated when you really look at it, but these are sort of field measurements, and the thing that really comes in here is that if you just look at face value as far as, okay, we've got resistivity, sometimes there's a correspondence with the waste, sometimes there's not, sometimes the material is high resistivity as opposed to low. So it's an indicator, it might work sometimes, and it has worked. But the IP just seems to be a more consistent thing for a whole bunch of different kinds of environments.
Could you say you need charged particles in the pore fluid in order to have IP?
Well, you will always have you always have ions in the pore fluid.
So it's polluted, you have maybe more of those particles than otherwise, and maybe that makes the difference.
That's the difference in concentration.
Yeah.
That's a good point. Well, we'll have to. So now I think this next case history might kind of resonate with you. So this is an area. It was a landfill for 10 years, sort of 100 meters by 100 meters, and it was basically sludge from some waste treatment plant. Had an estimated volume of about 65,000 cubic meters. But when they did it, there was no containment, there was no way to capture the leachate, there was no isolation of the system. They just dumped it. And the current state is that the landfill has got lots of iron, hydrocarbons, or organic. So they've done a fair bit of work. They've got some boreholes in here. They've taken some gamma logs. They've done some DC resistivity and so the general setup, and maybe there's parts of this that are kind of similar to what's happening in Poland. You've got sort of an upper clay layer in top couple of meters, and then there's a waste layer, and then there's sort of sand and gravel kind of interbedded in here, and maybe some Aquitards that are coming. So the aquifer itself is it's used for drinking, and currently the landfill area is kind of a away from the area where they're extracting the water. So it's not really of concern right now, but their concern was that if the water table actually raised up, that there might then be more of a connection and a lot of the material that's actually associated with this waste dump could come. So that's the objectives. Basically delineate the boundaries of the landfill and the current depth, locate a leachate plume, and then also identify lithologies of aquitards, clay-rich sand layers, and maybe a deep silty clay lands. So those are kind of the objectives. And the properties of these different units are given here. There's also a gamma log that was taken, and the gamma logs are basically associated with high values of, well, for the clays especially. The survey was a time domain IP, just like we talked about yesterday. So put the current on, voltage rises, turn it off, and then this decay curve that's coming in here, everything there is connected with IP. The IP data that they used is an integrated value of this secondary voltage over time channels, and so that's their IP data. There's 11 lines of data, and 20 gates per 20 time gates per receiver. So they had 25 boreholes, and there's a number of holes in here at which they've actually got the gamma logs.
Any idea what the first time gate would be?
No, they didn't say on that. So the inversion and processing is done. It's a little bit different than what we were doing. Yesterday I was sort of advocating a two-step process, and in that, basically at each time channel, we invert each time channel individually, and we get out something, sort of a pseudo chargeability. In here, remember I had that curve where people asked, somebody asked about that chargeability curve, whether that was typical or not. And I said, well, it really comes from a coal model. So here's a representation that's very common for the complex resistivity part. So rho naught is the resistivity at DC. M naught is the chargeability, intrinsic chargeability between 0 and 1. And tau is the time constant, and C kind of encapsulates the frequency dependency. So this is the description of the complex resistivity, and you can formulate the inverse problem so that you have a number of layers, and each of these has got its own suite of parameters. So you actually made the problem more challenging now, because now every cell has got 4 parameters that's associated. Nevertheless, you could proceed that way. And what happened is, if you take a DC resistivity section, or take your data and you invert it, then you'll get rho naught here. So here's your resistivity, here's your chargeability, here's your time constants, and here's your frequency dependency. So each of these, you end up now with 4 maps of data that are telling you something about what might be going on. The 2 that would be concentrating on just the resistivity and the chargeability.
The layer boundaries are fixed or also variable?
They're variable, I think, too. They have, well, actually, I'm not sure. Maybe they might be
part
fixed.
of the inversion?
Yeah, it's all part of it. Sometimes they set these problems up in such a way that the layer boundaries are fixed, and sometimes they set them up so that the layer boundaries can move. I somehow suspect that these are fixed, yeah. Because I think at some point I remember reading that they were doing 25 layers, which definitely would mean that they were fixed. So you can't read that. So the landfill area is this, and then there's basically four lines of data that kind of go through there. So there's listed up here. The important point is that as these lines go through, so the data goes through, they're inverted, and here's the chargeability section that is obtained through one line, another line, another line. And these arrows that you have here indicate, from a historic perspective, where the boundaries of the waste dump were. You can see that the Inversion for the chargeability has done a pretty nice job in delineating that. Now they can kind of interpolate the chargeability section and now get sort of a 3D representation. And then you could use a cutoff value, which they used here, 100 millivolts per volt. And then that gives them this as an estimate of the volume of the waste. And actually that number kind of came up kind of reasonable. It's like 50,000 cubic meters. Of course, that will all depend upon a whole bunch of things, what the isosurface level is and stuff like that. But as a first shot, that was actually a pretty interesting comparison. So that did a good job on locating and finding the volume. And then there was the aspect of interpreting the different lithologic boundaries. So the first one is a clay layer. So clay has got a low resistivity and a high chargeability and a high gamma. Okay. What we see here on the resistivity section is, so the blue is really high resistivities, and then the red is low. So if you look in the top region up in here, you see that it starts off blue, and then there's a conductive or low resistivity layer that's right in here, and that layer is also chargeable. So if we take a log that is sort of coming through here, and we plot it up here, what we have is the resistivity in blue. So it's highly resistive right at this depth, highly resistive at the surface, and then it drops down. So it's very low resistivity, and then comes up. The black line that's plotted in the background is the gamma log. And the gamma log sort of starts low, increases, and then goes down. So that's typical of a clay layer. You'd have low resistivity and a high gamma value. The chargeability does the same kind of thing in the sense that it actually has a high chargeability at the clay layer. And so it looks like that. So here, resistivity and gamma are anti-correlated. Here, chargeability and gamma are correlated. And you end up with a region in here that has got high gamma, high chargeability, and low resistivity. So you interpret that as a clay layer. Coming down into a more intermediate section, there's kind of a clay-rich, sandy layer that's in here. So it's this region in here. So it's got a rather high resistivity. So it's sort of sandy clay, but expected to have a high resistivity. The chargeability is expected to be moderate, and you see that in here. And the gamma should be fairly high. So if you look at these logs in here, that's basically what we're seeing as far as a correspondence. So we've got this relatively high chargeability in this layer and relatively high resistivity in that layer. And then if we come down,
the sand has a relatively high chargeability in this case.
It's because of the whatever clays that are in. So,
It's not like clean sand.
yeah,
There's a lot of,
yeah,
but it doesn't lower the resistivity that much, but it does increase the gamma and the chargeability. No?
Lower than the clay.
Yeah, but so much higher than the layer in between at 18 meters.
Yeah.
I'm amazed by the correspondence between the gamma and the chargeability. I like it.
yeah. So that's that seems to be kind of a nice indicator. And
Whereas the resistivity doesn't.
well, is the 1587, this log coming right through here. So the resistivity and is kind of corresponding with the high gamma. Right, so we go.
You could should be the other way around.
Well,
It should have a lower resistivity.
Yeah.
no, this clay layer up here, okay, has got a low resistivity.
Yeah.
Okay, so this is how I understand.
That's
So, okay, so you've got a clay layer, it's got low resistivity, and then you're coming down into another sort of formation that still has some clay, but there's a lot of sand, or maybe it's sand and it's got some clay in it, right? Yeah, so
Clay sand.
yeah, so that means the resistivity of sand is high, the resistivity of clay is low. You mix them up together, and you're going to be someplace in between. And I think there's enough sand. There's enough sand in here that the resistivity is high, and there's enough clay that the gamma is high.
I mean, you can also have cases where you have radioactive sand and the gamma is suddenly high. It's
Yeah, we have,
sensitive to
in
uranium.
Delft, we have chlorponate.
Yeah.
So chlorponate in the sand gives a high gamma.
Yeah.
I can imagine it also gives a high IP. I can imagine.
So what did you?
Yeah, chlorponate.
In green sands,
Yeah, green sands.
Oh, never heard that.
But they're a radioactive sand, like high uranium potassium chloride.
Well, I don't know whether they're all high, but at least.
Well, one of them,
Okay.
often potassium can make, in the oil industry generally, you can just say either they all know or not know, but very often you get very clear relationship, like high gamma in a clay and low in a sand. But on occasion you get radioactive sands which throw that interpretation out the window.
Okay.
And if you have it in the new surface, probably more often than you do a couple of times.
Probably. Yeah.
There are
Maybe to get a high IP, I can imagine.
Yeah. probably a mix
Anyway.
of clay and the
Yeah.
sand in the high.
And the rest of these lower curves. And zero and the gamma. Interesting.
And if you go down to that third layer, if they were looking for a silk clay lens, so they're looking for something that's low resistivity, high chargeability, and high gamma, and right at the bottom area in here, then we've got very low resistivity, we've got high chargeability, and in this region in here, we've got moderately high gamma values. So that was sort of an indicator that maybe this, in fact, region right at the bottom here is that silk clay lens.
I don't.
You don't?
Yeah, because the gamma is, these four holes are next one to the other. So I don't know the interval between, but maybe not. So much.
1605 is here.
Yeah,
So it's sitting up.
and then 20 meters away you have the other one. And if you look at the gamma, you say, oh, that's the same clay layer.
Each of those ticks is 50 meters on that axis below.
Yeah,
Actually see that. So this,
So it's 20 meters in between.
something like
It's the same clay layer, you would say, for sure.
Yeah, so this,
And the one is, so I don't know. I think it's too deep, too thin, too deep to be seen by the resistivity.
this does seem to be at the bottom edge here. So, yeah, I'm not sure what they use to kind of cut this off.
If I understand you correctly, you say from the gamma ray, you say it's the same clay layer,
Yes,
but then
definitely.
from the resistivity, it suddenly is different.
Yeah, maybe there is, well, but that is the resistivity not measured in the borehole. It's an inverted service thing, so I don't know what
Yeah.
it is.
I mean, the profile of that gamma ray definitely says the same profile.
Well, yeah, but that's interesting because maybe you can't see it here, but so there's a borehole legend here, right? And there's this guy here, so this is clay, so there's this pixel that's coming in here, it says that's clay, and there's nothing here for the red. So as far as the borehole log went, it does look like there's a difference between here and here, even though there's only 20 meters difference, right?
Someone should have
I
found
like
gamma
more
ray.
the gamma measurements than what the borehole people say.
Yeah,
One was on Monday, the other on Friday. Yeah.
Someone should have run resistivity in these. Well,
Yeah,
that'd
we
be
always do.
Yeah.
But still, I like the lower figures. So,
Yeah, and so this is kind of interesting up here. So if you look at, I mean, let's just take this at face value and just see what there is a bit of a difference here. So this is low resistivity, so very low here and high chargeability here, okay? But above here, the chargeability gets less, and above here, resistivity is also a bit higher, but it's still pretty low resistivity. The point about that might have some physical meaning and understanding, I think, is encapsulated kind of in this diagram that they put through, which is kind of a cartoon on what's happening. So here's the waste, and then there's that upper layer here, that clay layer, and they've listed that as an Aquitard. I mean, and the only reason that they gave for that in the paper was that, okay, we've got it as a clay layer, and then there's a stream up over top of it, so we're thinking that this is an Aquitard. I don't know if that's a sufficient, but that's basically what they said. So they listed that top clay layer as an Aquitard, and then they've got this clay-rich sandy layer coming in here, and a clay lens at the bottom, okay? Now, in addition to that, there's this pollutant, this contaminant leachate that's coming down, and it's, so it's coming down, sort of being truncated by this clay lens, and then it's moving up here. If that cartoon is true and we transfer that to here, then we'd expect to have higher conductivities or lower resistivities that are going outwards, sort of above the clay lens, which maybe is a bit more reflective of what this resistivity here is compared to that. So at least from the point of view of a story, which I can't elaborate, it's not our work. Everything kind of fits together, and when they do,
Is the brown dot at the bottom as a resistivity, is that a representative of the clay layer or a representative of the leachate?
yeah. So I think this is the thing. When you do the resistivity inversion, then you get something that looks like this. So here's the waste dump, right? And then you get this high conductivity or low resistivity. It's kind of a plume that's coming out this way, And that low resistivity can be caused by two things. One is it could be that clay lens at the bottom, but also the leachate is, it has a low resistivity. So this line, it's P4, if you cross that, so here's the result from the resistivity inversion. So there's this low resistivity blob that's sitting in there, and if you look at that line, that's sitting out here. So that's quite a ways away from the waste dumps. The waste dumps are right here. And then the next slide has taken this same thing and plotted out on a section. So here is this line that's coming through here is a section on which they've drilled a number of holes. Profile 4 lines right in here. That scale is a bit hard to read in this room, but this is really the highest value of the chlorinated compounds that are sitting there, and that matches actually pretty nicely with this guy. So there's, they've drilled through, they've evaluated the amount of metal ions in fluid. There's a lot of them at a depth that kind of matches where we are here. So part of that plume is definitely the leaching that's coming up. So I think that's good, right? I mean, this is a seriously tough problem, and they managed to go through. They've got a certainly the first. I think the first aspect of trying to delineate the boundaries of the waste and the volume from the IP has been that's really stable. The delineation of the leachate plume, I think they've made just by looking at that high conductivity, low resistivity that's coming out from the waste dump site. That's probably a pretty good interpretation. And then their assessment of trying to simplify the geologies and the sands and the clays into something that looks like this and kind of matches the gamma ray, the chargeability, and the resistivity. I mean, to me, that seemed to be one of the nicer stories that we've seen with respect to the use of IP. So I think IP has definitely got a real role to play here in landfills.
It would be interesting if they could indicate when a repeat survey would be useful. So how many years from now would you do a repeat survey to see how the plume has moved?
Mm-hmm. Yeah. Well, I'm sure they'll do that here because this is an area that they're actively interested in. Work at this point, so it's not, now it's like a test site, right? So you want to go back and check and see what's happening. Okay. Probably have a quick cup of coffee, and then I think about I don't know, 25 minutes or something like that for the GPR, and then we'll switch over and have people talk about some stuff that they're doing. Do people bring slides or anything? Because we could load them up here while we're having coffee.
Maybe.
Yeah, or just connect this thing.
Yeah.
Could be. Well,
we would, if possible, if you're willing, to capture it on video. In which case, it's easier if we have them all on one computer.
Okay, that's good.
Do you have? Okay.
I have a presentation. I have a paper that I just go through in a way.
That was just quick. Yeah.
Yeah.
So we're already with it. Maybe just starting up.
Yeah.
And then, if you don't mind putting your name.
Only if you give me the follow.
It's put up on Instagram, but I'm happy to also send you the.
Yes. Yeah, do that. Yeah. I don't know.
You might have to remind me the line.
I can send it to you.
It's written down.
Yeah, but I will send you an email to send this program. But at first,
So, did you have a pretty good idea about where you're based out of?
it's just to the right.
Yeah, that is all part of the nice alignment system and everything. It's part of the and they determine what layer that.
Oh, yeah.
So the boundaries are quite defined, but actually we want to use the liberty and the IP to map the nature content.
So when was the landfill established?
I think they started 40 years ago, and they finished like 20 years ago. So it's already covered with the lakes. They're collecting the leachate that's coming out, so it's still gas pollution.
Yeah.
So the liner that was put in, that was 40 years ago now? So that was pretty early in times for people putting liners.
Yeah, I guess, yeah, for 40, yeah, maybe 30 years old. Yeah, I guess that's regulation.
Yeah, and what kind of liners do they use?
The action is.
I'm not sure.
Is it fit or? We don't know. And then, so do they think that the liner is leaking?
Yeah.
Or the leachate is coming out? Or they're just trying to find the
We're trying to find the leachate inside, because we're trying to send it to Louis. So we
So why
want to
is
clean
it-
up actually.
But why is it?
Yeah, so in that sense it's not polluting, but it's still producing strong leachate and gas. We want to clean up the area so that we don't have to capture the leachate.
So where is are you capturing the leachate from outside the liner or from inside?
From the side, the liner, the top of the drainage system, sending the leachate out to the drainage lines.
Oh, okay.
So nothing comes out at the bottom.
Yeah.
But now for regulations, I have to do that 50 or actually for internal traffic, they have to extract, capture the leachate.
I tried this, and it doesn't work for
Now you can leave the landfills, so you have to worry about aftercare. Getting waste.
I realize this doesn't work when people using it. So I changed the reference by I think we have the current monitoring requirement. Rolling reference.
There, but
That's the reason
You're gonna talk about all this, right? You're gonna talk about all this.
yeah, no,
Yeah, so, well, I think it was,
Okay, well, do it.
mostly work. I think it has to do with the fact that from well, even
the big difference between
Pure matrix.
So all the metals is in there.
So it's like those aspects of
I show that in every single case, cross-correlation.
They actually contacted us this year because they want to do some seismic or university has, but we couldn't give it to them. Research interest for us, bring it all the way to but then they, maybe
yeah, exactly.
So with we help them with the brand. Next year, they will more. They do that every year.
Okay, well, we're trying to find
I don't think my research because also in seismic that it was like a map, like a zero.
Yeah, I would set it. Take something, make it good.
We use like 12
Okay.
I wouldn't do anything else.
Yeah.
Well, and yeah, and the thing is, just because nobody does something doesn't mean that it's not a useful thing to do. Nobody has done it.
Yeah, and then on the lake we have yeah, sometimes
yeah, so that's how I feel
oh yeah, so for the purpose, yeah, we want to see
So how far along are you on this project? Did you start it?
Yeah, I did a PhD or a satellite project. So the last 4 years, 5 years, I got 2 PhD projects in this project. But I did mainly that's also my background, so I was learning there was another reason now seismics and ER2 measurements. graduated this year. Now we continue with projects.
I prefer that we should have
very much
it's kind of like
infrastructure and we made a model to predict the emission potential
bit more to the
and then we will do a line information into measurements, the water content mapping, or at least we can also measure temperature in the basically, we during the last 4 years, infrastructure. We just started installing everything, and then we started.
Well, and there's certainly really interesting things that come up this morning with respect to, okay, the what's actually determining what happens with
They say something about this paper about
no, not really. No, it's not that. The paper with the time lapse just sort of gave this as an example. It was just like they were trying to kind of showcase and I got a little pretty so we captured that. I thought I didn't make sure it was fine. And it's like it's a no-brainer, right? Waste out there. And this is what
that's like you tell me, like
I think that are Parcel, I think it's and then when we're to Taiwan, oh, wow. That's kind of fun. And dog so I'm gonna go to the washroom and I'm gonna come back. We're gonna That's okay. That's okay. Yeah. Would you mind if we we can make it private. We're trying to capture this. Okay. And even for our
cycles of pressure, and then when they drop it, it's like a method of monitoring pressure without. Well, I suspected that because it's a scatter landfill, you end up with the majority of shear waves. So you end up with dominant shear wave energy. The transducer says otherwise like this. Anyway, you can call it anyway. But of course, it's also getting energy from all directions. So it's recording all shear wave and compression wave energy. If I would, I did experiments you see the same thing. The only difference is that we've got a polarizing energy from motion. It's not such an issue because it's a scatter wave, right? The energy is coming from all
But without doing the theoretical go out
No, but he's written papers about the whole topic. The transfer coefficient from P to S, and to describe how you end up with in a motor, you end up with a dominant shear wave because two reasons. One is that there are two modes, let's say, of shearing, like you just say X and Y, and also that there's a higher probability that energy converts from P to S than from S to P. So in the coda you end up with a majority shear wave energy over time, even if your source is P. So the motion of movement is predominantly shearing in coda. That's also, I think, something also talks about. But roll shear derives some sort of.
But the difficulty is we miss the connection of the people who change behavior. I mean, you can follow the literature.
Yes,
very willing to answer questions.
Well, see, all you're doing is discriminating between
if you're working on reliably,
direction. We don't know whether the wave was necessarily a compression or a heating. The problem is you've got this sensor,
that's
and if I have a purely compression, of course it's sensitive. But if I have a compression of the flight, right? But it's also still, if I have a shear like this, it's also got a sensor. So you see somewhere here. That's the problem. I don't see quite how you make a distinction between what actual rows are.
Yeah, when I was PhD student, I was working in one course in Japan. And I did a full correlation spectrometry. I did this.
Did I just make you a job? Do I get like 10% for blinders?
Yeah.
I was not sure that this
it's quite hard. It's a kind of a bulk velocity. Velocity property that you get
Oh, thank you.
So you have velocity because it's stronger than more energy than shear, the less.
especially with these
Just because of this transfer coefficient. Transfer coefficient showing this elastic wave higher from S than SED, which is like a probability. Statistically more likely than the more volts, the higher the so I think that's why you have PhD do.
It's not really like
That'd be great.
okay.
Okay, what we're gonna see.
There's a lot of scientists in the world. Reflections.
We'll just maybe pass around videos and for anybody who is planning on doing a presentation.
Okay, so the plan, I'll just do a quick run through on GPR just to kind of round things out and maybe bring back a few points of discussion. And then we'll flip over to presentations from people, and especially Andre with the landfills, because he needs to go stuff. Because I think there's actually quite a few things that are coming up with respect to use of IP for landfills and monitoring. I think there's a huge potential for some interesting scientific questions, and also we'd like to find out a bit more about what you're doing. Okay, so again, we always need motivation, in particular for GPR. It's basically shallow work here. It could be sinkholes. Saltwater, freshwater interface, there's been applications for there. A lot of work done in very near surface engineering, geotechnical work, for finding underground tanks, archaeology, that's what we're doing, and rock glaciers. We have a case history on that. I probably won't go through that. So just to kind of briefly go through the basic experimental physics, bit of data processing, not very much, pretty rudimentary, a couple of field examples, and talk a bit about the driverless vehicles, but it's small. Anyway, so this is the basic unit. We have a transmitter, receiver, so this looks very seismic oriented. In fact, all the pictures here could be, sort of a seismic instrument, and we've got rays that are kind of coming down, they're reflecting off, there's stuff that's being transmitted, and in the end you're going to be plotting radar grams or signals that will look pretty much like a seismic section. So the basic equations we had yesterday, but now the thing that is on grade is this quantity here, which is the displacement curve. So this is really the wave propagation curve that comes in when you make a second order system. And we showed this yesterday, take the first order equations and put them together, and now you get something. So this looks very familiar to people in seismology. This guy here is a bit of an annoyance in seismology because it's attenuating things. But what we did, well, everything we did yesterday, because this is so big, basically sigma and over omega, it's much greater than epsilon. This guy, as we usually ignore, but we're not going to now. The quantity of interest is the electrical permittivity and the velocity of the electromagnetic wave is the velocity of light divided by the square root of the dielectric constant. So the dielectric constant is really the ratio of the electrical permittivity of the material divided by the permittivity in free space. When you do that ratio, then you get an epsilon, which we call dielectric constant, which basically varies between 1 and 80. And it's water that is the big kid on the block. And it doesn't matter if it's freshwater or seawater, it's a high dielectric constant. We talked about skin depth. In the quasi-static regime, this was the skin depth formula that we used, so we used that all yesterday. And if we look at the skin depth as a function of frequency in that quasi-static domain, it's looking like this. But if we increase the frequency, then now the wave equation term starts to increase, and we end up that the skin depth kind of asymptotes out here and doesn't change nearly as much with frequency. So that's basically the curve that tells you how much things are going to attenuate.
Frequency above 10 to the power 8, you might as well talk about wave propagation.
That is correct.
And below it, you talk purely about diffusion, or is that a combination then again?
No, it's really, for most of the problems that we deal with, like 10 to the 5th hertz is kind of that sort of boundary.
Boundary for diffusion.
Yeah, so everything back up here is diffusion.
Okay, so in between it's...
It needs both.
Okay.
We have an app. It's electric dipole in whole space. This one's really pretty interesting to use, and it solves the full equations. And you can look at different frequencies. Here's 10 to the 5th hertz. So this is what the electric field looks like, and at 10 to the 6th hertz, you can see how much extra structure it has, and you can go ahead and you can count, the number of periods that are going in here, and actually convince yourself that, oh, this relationship of lambda over EF is actually in accordance with this result. So it's kind of interesting just to see what that radiation pattern is from that.
So you talk about near field and far field in this sort of cases, that the far field is maybe more structured like wave propagation than the near field?
Yeah, I think that's good. So in those high frequencies, then, we do have kind of take this path, right? So we've got direct waves in the medium, we've got air wave that's going to travel at the speed of light, we've got reflected waves, and we've got waves that will come down, bounce back up, and then they get refracted at the Earth's surface, and then go this way. So the refraction is kind of interesting because the highest velocity is actually here in the air, and so the major refraction is kind of coming there.
And you can talk about surface waves.
Well, not in the same sense as like Rayleigh waves or Love waves or things like that.
That's
I don't think so. It just doesn't. But
I could imagine the sort of interface wave, like in seismic you have a slaughter wave, maybe something like that. But I don't know.
No,
I haven't heard about it.
I haven't heard of anything like that.
It should be then. Or can be, maybe that's low amplitude. No. Interesting question. So what this movie is just the wave fronts. So you're setting off an impulse, and you can see. So there's the wave in the air traveling at the speed of light, and you have this guy coming down here, it's reflecting back up. Now, it's some of it gets propagated through, and then goes out. So those are, wave fronts similar to perhaps what you're used to for seismic waves. Yeah, so we've got these different ray paths, and you can kind of see what the associated wave front is. But the funny thing is, if we do this for full elastic waste population, we get service roads. I'm curious what the difference is now. If we make a movie like this, you can see the service roads in full elastic modeling. Yeah.
Right, but I mean, we don't have particle motion. I mean,
No, but particle motion is like a field.
right, so we could get,
So,
Something like some components should be zero from the bottom.
yeah, maybe that's the case. Yeah.
It's simply the layer boundary. I don't think
I don't know, we'll have to check.
Yeah, we
Is there any such analogy here? For processing, because you're working at such high frequencies, you're hundreds of megahertz to a gigahertz, right? Even if you're pulling the instrument along, it's recording, thousands of realizations of your signal at each time. So you can afford to do a lot of stacking, and that allows you then to gradually, beat down the noise in favor of some signal. So that's a big thing. So stacking is important. The other is just countering the geometric decay of the signal, and there's usually a gain function that is applied. So probably familiar to seismologists, and stacking, apply gain, and get out a radar signal. And here's what the typical radargram would look like. You can see that there's some reflections, horizontal reflections up in this near surface, and then there's these hyperbolic types of structures. So those hyperbolic structures are obtained just because you've got a source and receiver that are moving across here, and there's some kind of reflection that is happening, and as you move across, and it's just the thing you're used to with seismic travel times that tell you when that pulse is going to come in. So there you have your source going off. Now it's going to reflect off of this. Come back here. So you can get, if you measure these slopes, you can get the velocity. And if you know the velocity, then that relationship between the velocity and the speed of light and the dielectric constant allows you to get epsilon. So just some examples of what that looks like. So here's some radargrams over, a number of tanks that are there. So there's tanks, and there's also a bed underneath so that the tanks are sitting on the bed. And the radargrams, as you go over, tend to look like this. So you can localize the tanks, and then these things here are beds that are sitting underneath. You can use these, they come in various frequencies. The size of the instrument, or really the antenna that's in the instrument, is inversely proportional to the frequency that you're working with. So if you're at a very high frequency, in the gigahertz, you can make the whole system looks like this. And here's a guy looking for cables, I think, underneath. So he's got his grid, he kind of moves his on here, and he's got a display up here. Kind of in real time, you can figure out where the cables are. Here's an archaeological experiment. You can also have the antennas not in a closed box, but they can be separated, so you can actually do like a common midpoint type of survey. That's actually useful for estimating what the dielectric constant is in this region, let's say right above here, and then you've got a conversion from time to depth. So just the same as in seismic, it's easy to get something in terms of time, but really would like to have it in terms of depth. So you need to know something about the velocity. So you can do a common midpoint experiment, get information about velocity, and then use that to convert time to depth. And yeah, this is the more common one. You've got everything in one box, and you're just moving it along. So it's a common offset or almost zero offset. Here's an example. This was actually just at UBC to look at what the underlying structure is going to be. And there's both DC resistivity and GPR that are taken. So the idea was to try to see if you can find out something about the lithologies and maybe water content. The line here was the GPR system, went along on that in a kind of fixed offset. Here's the radar that okay. So you can see there's some horizontal reflectors in here. There's a couple of objects that are giving rise to hyperbola, and there's a blanked out region in here. So that's kind of interesting. Like, why are we losing? Why is the signal so poor in here compared to here? If you then subsequently go and do a DC resistivity survey across here and invert that, you get a resistivity map that looks like this. And this red region is low resistivity. So low resistivity means that there's going to be more attenuation. So this radar signal is actually attenuating as it goes through here. And this map here and that corresponding resistivity map kind of helps understand what's going on. Yeah, so here is another case, or again, here's the tanks. I kind of showed you that before, and you could do, you could take the radar grams in, and do it all in kind of 3D. So you've got a 3D volume of radar grams, and then you can convert the time to depth, and now you've got particular depth slices. So at 3 to 3.5 feet, you see this. At 5 feet, you see more of the this bottom tank bed and what's going on over here. You could use it to map peak thickness. This is an example of somebody who's just towing a system along here. This was in Ireland, and yeah, just tow the system, keep track of where you are with the GPS and some kind of a wheel counter, and you get a system, get a result that looks like this. So you can tell where that peak layer is, and they actually mined this in Ireland. It's
#1 source of heating in Ireland, you wouldn't believe.
Is it still?
Yeah. Oh. They still go and dig peat and burn it. #1 source of heating. Not in North
high
Ireland.
carbon footprint.
Yeah, I know. Yeah.
It's not for the whiskey then.
Probably also.
Ah, yes. Now we're talking. Good, nice, smoky whiskey with that Scotch. I kind of showed this is kind of like another utility experiment, but there's two things. One is there was an iron pipe which is very conductive, and then there was a PVC pipe. But both of those will be a reflector. So whether it's metal or whether it's water, they will both show up on the radiogram. And so that's what's done here. And they actually were able to distinguish the two pipes, the natural gas one at 1 meter and water line at 1.4 meters. So really, really useful variety of extraction. Here's one where it was used for water in setting. This is a potash mine in Saskatchewan. So you're always worried about, okay, water is coming in from the top, right? So you have to do the experiment where you to putting the radar unit sort of up on the ceiling, which interestingly enough, they call the back. It takes a long time to figure out what that was. But yeah, put up on there. So that was it. Oh, I kind of showed you this the other day, but this, you know, I just thought this is so cool. And it's actually one of these things that I think are really important for connecting with, you know, the average guy on the street as to, you know, electromagnetics. And yeah, it just kind of resonated, and I wanted to show it. So the idea here, this is work that was done at MIT with the Lincoln Labs, is that they're concerned about what sort of sensors can be used for cars, especially in bad environments. So here's it's a bit of an older picture, it's a bit of an overkill, but here's the car, and you know, you've got where the car is with respect to everything else. So you've got a GPS, you've got a LiDAR, you've got a camera, and you know, these things actually work pretty well in good weather. But in bad weather, when it's rain or sleet or snow, or you know, something unexpected has come in, something's been changed, or even if somebody is running out, if something has been changed, you might be hard pressed to make sure you know exactly where you are. So the idea was like, okay, could we get more, you know, another sensor? And the question is what you could do as far as having something that doesn't change with respect to those weather conditions. And so the system they got, this is that MIT truck, and there's a GPR unit that is sitting underneath here. And the idea is to kind of do this in two parts. You have the GPR system there, and then you run the car over the road, and you collect basically a radargram of what that road looks like, okay, in good conditions. So you collect these data, you store them as a reference data set, and then that's your that's your test data. So now you come along with your car in rather poor conditions, but you can't maybe see, your optical sensors are not working so well here, but you can still see into the ground. So it's it's shallow, but you can see down, and that region is not really affected by the fact that there's a little bit of rain or there's some fog or something like that. So now you get this radargram that's coming in, and you do a cross correlation of this signal with their library signals and try to find out the northing and easting location in which you've got that highest quality correlation, and then okay, this says at this particular moment in time I'm really at this spot here, and that's.
Were they able to drive on that data?
Pardon me?
Were they able to drive just on that data? So to drive along a certain stretch of road just on that data alone?
Next application.
Like I mean, like, okay, I understand the principle, but is
It's great to collect the map of the road. Like,
yeah, it's great for civil engineering, infrastructure monitoring applications. But my question is,
when there's sleet, there's also salt spray.
Yeah, so I was wondering, yeah, it's a bit of water, or it needs salty water.
but they would be looking for the part of the radiogram that's deeper as a correlation, hopefully, and that still remains high, correlation with the reference library.
Yeah, you can get that deep.
What's this?
Yeah, I got it.
Yeah.
But it also opens up for the whole public, the whole concept of like, okay, maybe we could somehow peer into the subsurface and, electromagnetics. I mean, it's got all the things, right? Electromagnetics, peering into the subsurface. And once you kind of break down, that barrier, then the whole thought process of, oh, well, maybe we could somehow go deeper and find this. But it's
well, people can use this data. Say infrastructure management in the Netherlands it costs a lot of money, and they put a lot of. So the Netherlands has some of the best rates in Europe, and they put a lot of money into it.
Yeah.
But that would mean that they would be able to monitor, and actually even Elon Musk already suggests. I think they already use automatic pothole recognition to then alert authorities that there's a pothole needs to be fixed.
Yeah.
So that the recognition from a camera, but this would be sinkhole recognition, degradation of maybe some cables. So that data set, if it's publicly available, would be massive importance to regulate the authorities.
I mean, just so many applications, and there's also just the whole mindset. I mean, people generally have, I talk to them about what we're doing, and they're like rolling up their eyes, right? And
but that's a very tangible application.
Exactly, they can relate to that.
But here in the Netherlands, they plan to use the, like in my neighbourhood, for example, there are many, many electric charging stations, and they're provided by the council. So the cars come and plug in, and they're used as off-peak storage. So the electric battery is used to charge in like say low consumption times, and then disperse part of their battery charge when the grid needs more power. So that circumvents the problem of renewable energy storage.
And you've got
that already exists in The Hague. They've already started to develop that network, but this is just another application of the electric cars, and then on top of the instrumentation that comes with it, a huge data set can be used. Hopefully not monetized by large companies. That's what Tesla are trying to do. That's why every single one of their cars has released now have a full automated driving capability, because they want to acquire a huge data set of roads, which is what will be needed by all the other car companies who don't own that data set. So because you need that to be able to drive autonomously, you need to have this digital rails, they call it. To be able to position your car accurately and drive on a highway. And if they are acquiring this huge data set, then they have power over other companies. Hopefully that someone regulates it and says you have to give it to the authorities.
But still then, you can best buy shares in GPR antennas. Every car has to be with a GPR antenna.
Lithium, GPR antennas, and cobalt. Those are the things you should put your money in.
So I just want you to know, you heard that from me. It's like the finder's fee. Yeah, I just want a little bit of the action. We'll go on to this. Your problem with the landfills and stuff. But the other thing that I found really, kind of inspirational over the last couple of weeks is when you turn on in these news podcasts, and they're talking about the hurricanes that are coming. I mean, so they're a disaster. I mean, they're just hugely terrible in that respect. But the positive aspect was from a Canadian viewpoint. We were looking at the projections of where Hurricane Harvey and now Irma, and especially Irma, it was going. And they started watching Irma like a long time ago, and then they were showing the projections from these models. Okay. And so the guy is up there, he's talking about, there's different models. There's a US model, there's a European model, and he's showing these different trajectories. And exactly, they were just really, really different. But they started off, excuse me, the same. And there was clearly a whole bunch of other tracks kind of in between, but initially it started, and then they went away. And then a day or so later, you can start to see things, still diverge. And then at some point, they both decide, okay, no, we're going this way, right? And just that whole concept of kind of uncertainty and predictability with models, like, okay, the models aren't always all right all of the time, but there's certain levels of confidence that you can make if you get enough of these models, and they're all kind of giving you the same thing. And maybe
the way I read it though in US media was almost like they were putting it as a competition between who's right best, because I watched the US broadcast on explaining Irma's arrival into Florida, and they were saying like, and this is the American model, this is the European model. It's like they're under competition.
I mean, they are, right? You want to be right.
I want to see this. But you see, all the modelers are thinking, oh God, because, yeah, I don't know. Actually, I think maybe it went a little bit left of California, not right. I don't know which one was left or right, but
Florida.
Yeah, like left on Florida or right. But the point being that the modelers know that their models are essentially, the uncertainty in that particular exact position is quite high. Their model could have very easily produced a right trajectory or a left trajectory.
Yeah.
So,
and you would like to see the overlap.
Yeah, and then the uncertainty figure on top of it.
No, but there is some insight about uncertainty just because you're showing these different things, and I think that's great, because politicians, everybody's, like, okay, tell me exactly what it is. But here's a case where it's been proven, like, it's very valuable information that's come out, and there is, clearly some variability in what those predictions are. Those get worse as time goes on. But you set the standard with something like Irma, and then you start to think about global climate modeling and stuff like that. And when all of these climate models are predicting sort of some of the same kind of accentuations in the ups and the downs of climate, then the public can start. I've sort of seen that maybe that does work. Maybe there are a lot of models, but by the time in those places where the different models are agreeing, that actually turned out to be what had happened.
Yeah.
And so I think it's just overall really good.
But there's also the circumstance in Italy a couple of years ago, seismologists were thrown in jail because they gave a low likelihood of an earthquake. The earthquake happened, and then the authorities were getting a lot of heat because a lot of the money that was meant to go into reinforcing buildings just went into politicians' pockets. A lot of corruption in that part of Italy, and the authorities threw the seismologists in jail.
That was terrible.
And then there was actually from here and other European groups putting a lot of pressure on the local authorities to release these people because it's ridiculous. So as long as it doesn't go that direction, like the public are like, what, your model said this and it didn't happen.
Yes, but this kind of reinforces that, right? Because the models are clearly different, and there is some variability between the models, right?
I didn't say the model says.
Yeah. So I think all of those kind of set the right framework.
Yeah.
Mental. Yeah. Okay, Andre, you want to give us a chat?
Yeah. Yeah, no, I didn't prepare a slide.
Perfect. But you're all right if we capture your talk, is that okay?
Yeah, sure. And then maybe I can use this.
Yeah, absolutely.
There's
yeah, well, we have been working on landfills the last couple of years. And maybe first, several landfills in the Netherlands. And they're actually old landfills which are already filled and kept. But we want to clean them up. And I first will give an impression of how the landfill looks like.
I had one that was there's one on the desk here.
Yeah, it's basically a hole in the ground where you have the waste filled and then some more covered on top, so you have a bit of a hill. And in the Netherlands, in these landfills, they put first in an impermeable layer. So actually all the rainwater that is coming in, is filling up with pollution, so it's produced leachate, and then here in drainage tubes, it's collected all the time because we don't want to pollute the environment. Only, this leaching process is very slow. So the way it looks now, we have to collect and clean this leachate discharge for the next 50 or 100 years. So we want to clean the landfill up quicker with treatment methods. So the leachate is clean, so we can just release the landfill. We don't have to care about collecting this discharge.
And you're saying that this was actually put together like 30 or 40 years ago? With the liner? And
the liner before we start filling, and then it was in operation for 10 years, I think, and then they kept it off. And it's already, there are many like these type of landfills in the Netherlands, which are there lying around and need to be treated.
But that seems to be so progressive, at least from a North American standard, that you'd actually put a liner in and put some pipes in to get rid of the leachate. I mean,
well, they incinerate all the waste now here, so.
Yeah, now they even go
further, like
the
landfills
all
that
incinerate.
were made 30, 40, 50 years ago. They don't have drains, etc.
No.
But that's a whole different kind of problem.
Yeah, you have also many landfills without drains systems.
So this
But these types are also already 30 years old or so, I think.
And what were they putting into the landfill?
Organic waste together with some industrial waste and some residues, slip residues. It's a mix of these things together. So there can be all kind of material inside. And what they are now planning to do the next 10 years is to apply two types of treatment methods. So they drilled holes in the landfill, and they're gonna aerate the system. So introduce oxygen, so to enhance the biodegradation, to enhance the leaching, so that the organic matrix is cleaned up faster. And in some landfills, before they start doing that, they will recirculate the leachate. So they put it back on top, and then it funnels through, and then the leachate is actually treated in the waste itself. It's really degraded. So in some of them, they first do the leachate recirculation, and then start the aeration. In other ones, they start the aeration immediately. I've been, for my PhD, I've been working on modeling this type of behavior. So how the leachate loads up and how what kind of leachate you get in time. And we developed a model which actually is based on the hydrology and the biodegradation inside. And it predicts in time what the leachate quality will be. And it's important, well, of course, with certain uncertainty, but it is important to have these models to be able to at least indicate that the leachate quality will remain low after the treatment period. So we want to improve this. We have a basic model, but we want to reduce the uncertainty in the modeling, and therefore we need more data. So that's why the next 2 years we want to focus on getting more data through ERT or DC measurements and DTS measurements. The other one is distributed temperature sensing. So while they were drilling the holes and installing the aeration filters, we co-installed electrodes at every 2 meters in each well, and we also connected optic fiber along the well so that we can measure temperature. And temperature gives information about enthalpy, so information about biodegradation, and hopefully it can also give information about water flow, and hopefully also the DC measurements can give information about water content. Because one of our main hypotheses now is that the water that goes through, funnels through in preferential flow paths. And you also have zones where water is retained, which is more or less more immobile water, where most of the degradation takes place, and then you have an exchange of compounds from these bigger immobile water regions towards the faster flowing water. And that's also one of the bigger uncertainties in modeling, so we would like to have methods to map how the water flows through the landfill and where the bigger immobile regions of water consent are and which are more dry regions in the landfill. So yeah, the last half year we have been installing these electrodes. So we basically now have a grid per pilot. We have 4 pilots where we just have, yeah, here you have then the boreholes. And you have, yeah, we have electrodes every 2 meters. The depth of the landfill is on average, I think, 16 meters. Yeah, 16. 16.
16.
16.
Okay. 60 would be.
That would be very deep for and we installed the optic fiber, which is connected through all the wells, so we can measure the temperature over the whole cable at once. And we are now trying out test measurements. So for the ERT, so we lay a service line along one line of boreholes, and then we try to do a spacing of around 2 meters with service electrodes and connected the whole line and trying to get images. But actually, we are still looking at trying to find the best DC or maybe IP method to capture water content.
So the electrodes in the boreholes, are they going to be used as currents or just voltages?
Yeah, they can be both. Yeah.
Is that what you're planning?
Yeah, it seems to me that to us that intuitively, if you can make sensors, so a pair of currents and a pair of measurement electrodes, and you scramble it around through the whole system, and then you get a current field or a different current mapping density, let's say. So you get more and more information, but I don't know if that's feasible or realistic. Yeah.
So are all your electrodes hooked up into a single circuit so that you could actually fire things off so that
yeah, we can measure now
these two electrodes, I'm going to measure the potential between these 2 electrodes with these other 2 electrodes being the currents.
Yeah, that's something we have. We can connect 196 electrodes at once. So we cannot do the complete field, but one line. Yeah, we can hook up all the electrodes at the same time. And then
you activate 4.
Yes.
The 1.
Yeah, I think. Yeah. Well, master student
relative to simple.
Yeah, I think master student has been working on trying to find the right combination of injection and measuring points. And for now, he keeps 1 pair of current electrodes, and then he picks 10. Well, you can measure different points, the voltages. And then he goes and does it at many different points, and then then we pick another injection point, and then we measure again. But we're still, you have so many possibilities in that sense that
there was a lot of work done on monitoring CO2, where they in Germany monitoring the CO2 plume with borehole electrodes, and they did a lot of assessment on the best configurations for monitoring this plume movement over time. It was over years.
Okay, sounds very interesting.
So that, Florian Wagner is the guy who was doing that work for his PhD. He was a student of Hans Rüdiger, and so he now works in Bonn, I think. So you will meet him there, but he will have a lot to say about what's the best configuration, because that was part of his PhD.
Okay, nice.
That probably be the same configurations, and they had only 4 wells with 20-something, 30 electrodes per well. They're deeper, 900 meters or 600 meters. But they were able to map the movement of the plume over time with the method.
Nice.
So I think
Okay.
the same sort of application.
I will definitely take a look at that.
What kind of electrodes do they have? Because if you use them as current electrodes, I guess they would corrode.
Yeah. Well, yeah.
And the deeper electrodes you cannot replace, so it's.
We installed now for the top we have just the pins, stainless steel pins.
Okay.
But in the boreholes we installed carbon fiber electrodes. That's something new we wanted to try, and we didn't. Yeah, we want to have the system working for 10 years, so we were looking for something that doesn't corrode that quick, especially in leachate. So what we made is it's a copper wire connected to well, a wire of carbon fiber, and then this connection we connected and we sealed it off with blue hose and really kind of sealing system to make it as watertight as possible, because this is the weakest link, we think. And then this is just a long fiber of carbon fiber, and we coil it around, not around the fiber, but around with the aeration filter in there, which is a PVC tube. And then actually we coil the carbon fiber here, and then the copper wire goes up, and that's connected. So in terms of corroding, it would be good, stable. I don't know if it's gonna work very good for injecting current, but until now it works. But yeah.
I think in Ketsin, when they were doing the CO2, they didn't have actually a lot of problems with corrosion there. Like most electrodes after 4 years are still working fine. So I don't know, it's leachate.
Yeah, it's quite reactive stuff.
Yeah.
And maybe it's not a problem.
Yeah.
Just to be sure.
If there is a concern with respect to using an electrode as a current electrode, and then soon after using it also as a potential electrode. So you sort of need a certain time for the electrode to calm down a bit. And,
because it's charging itself.
The charge itself.
Okay.
So when we talk about monitoring the quality of the leachate, what do you actually refer to? Is it just that number of total dissolved solids, or what is it that you're? How do you know when your leachate's clean?
Yeah, from the government there are certain regulations about the highest concentration that compounds may have in the leachate before they enter the environment and the groundwater system. For most of the compounds, that's okay. They are below this threshold value, but some of them are way too high. So that are the ones we are targeting on. That are, for instance, the chloride concentration needs to be diminished, and the ammonium concentration is too high. And chloride, yeah, you have to get it out by dilution or by leaching. But the ammonium we could be removed by the aeration treatment, because then you can oxidize ammonium to nitrogen gas and then put it.
So how do you get rid of the chloride through leaching?
Yeah, one of the there's a certain pool of chloride inside, and if you just supply enough fresh water, then you just leach it out. Right, and then in this phase we can still capture the leachate and then treat it, and then
you're going to just keep recycling it, right?
Yeah, so
How do you eventually get rid of it?
there will be a bleed stream and there will be fresh water added, so it will be. It's not
Before
pure.
you put it back in.
Yeah.
Cleaning the leachate effectively as you put more in, as you put it back in.
Yeah, or we take something out and we dilute it a bit on the top with a difference. It's not a 100% recirculation.
And any plans of using other methods to know exactly what's in the, or as best as you can, what is in that volume? Because part of it is modeling, that you need to know what's in there.
Yeah, there are not that many methods which allow you to look into the landfill. I mean, while they were drilling, we also took solid samples.
Sure.
So we will analyze those, but those are 35 borals on 5 hectares. So it's
Any suggestion that what sort of method you would be using there? IP or GPR? Or?
The CPT tests, the equipment gets now they are able to put more and more sensors on CPTs now. Magnetometry sensors, cameras, light, and CPT testing is fairly cheap in Holland at least.
Is that penetrating?
Yeah, penetration test.
Okay.
Yeah.
So the penetration test itself can give you information, but also if you put a magnetometer sensor on it, it can give you information. Or, I don't know. So things are developing more and more, so that might be, and relatively cheap, of course, because if you do a destructive coring and take samples, that's pricey.
Yeah. Okay. So that might also be interesting then. If it's not too expensive.
It gives you more information. It won't give you the solution or make your model exact. But it's an extra layer of information.
It would be very interesting. Yeah, if we do this and get something out and then do an additional round of CPT tests on different locations. That might be very interesting.
So what do you think the conductivity of the fluids are, the real heavily contaminated leachate fluids compared to the general groundwater that you're pumping in?
I think we have on average 10 millisiemens per centimeter conductivity, just per meter.
So in terms of ohmmeters?
Or students experience, so what is it, 10? Would you say
millisiemens per, I think per centimeter. That's the main. So that is.
Oh, so that's 10. Oh, so that's 10 minus 2 siemens per meter. That's not hugely conductive. So that's like 100 meters.
Okay.
Right. I didn't know that.
That's kind of but yeah.
Is 1 over
10. Oh, 10 millis. Yeah, so it's 1.
So it is it conductive or not? Yeah, I know that good feeling. Yeah,
that's good.
Yeah. So on this basis alone, I think we should be able to map at least drier and wetter regions in the
The drier and wetter regions, GPR models also show that.
Okay.
Yeah.
I guess.
Yeah, but really, you're kind of replacing your leachate with fresh water. Makes sense, because you're continuing to pump in fresh water, right? And you're just taking out.
You have the rain supply also, which is also fresh.
Which is considerable.
Yeah.
But concerning GPR, you have a cap of treacle plots or some kind of clay layer.
It's clay. the soil.
So
Yeah.
we use a low frequency radar, and then the resolution will be window. So
You have the airplane on top. Forget about it.
Yeah, how thick is that clay?
Around 3 meters.
Oh, that's
Oh.
thick.
Yeah.
Okay.
Other methods that, I mean, these results from this IP measurement, at least there's quite some difference before and after the treatment. So,
Yeah.
if I can find
And
out
this
what it,
configuration we use to do the IP check.
yeah.
Depends on your instrument, huh?
What
No,
you
but
hook up the
you're
electrodes to.
taking, yeah, a DC measurement, right? So presumably you're just using traditional kind of square wave, so it's on, it's got off.
I think IP is.
Your system's all set up to measure.
Yeah, we use the iris system. I think it has options to do IP. Then,
At
at least
16 meters depth, you should get a reasonable resolution, I reckon, or not?
Well, you've got boreholes. How deep do your boreholes go?
well, 2 meter of the above the base layer, so yeah, for
Yeah, but you're going to get a lot of coverage.
But yeah, the difficult part is that it's very heterogeneous medium. So yeah, the inversion will be tricky because you have very conductive material. And,
What's the distance between the boreholes?
15 meters.
15.
But from the point of view of determining how well you're doing with respect to reclamation, then it's really a time lapse that you're. So there's some aspects of, some complications that go out just because you're using time lapse, using differences.
Yeah, we're also thinking about it. It might help, especially also if we have different pictures of saturation of the landfill, for instance. So if you have a dry period, then most of the leachate is leached out. You have a dry landfill, and if you measure the same amount of waste after a heavy rainfall event, I think you should be able to get a different sensitivity.
if you consider the OMAR by geometrics, it's a long cable, 10 meters or 20 meters, or with transmitters and receivers to measure your resistivity. You just pull the cable along. You don't have to put stakes in the ground or whatever. You just walk with that 10 meter long or 20 meter long cable along your landfill.
Okay, I think that's nice.
I'm not familiar with the depth, but
Well, the depth will be a fraction of what your longest spacing of
Yes,
between
yeah,
your
of
current
course,
and your
of course.
potential.
I know in France, for instance, they use the OMA for landfill surveys. I don't know what they were exactly looking for, but you could.
It sounds really
Yeah,
interesting.
OMA
And how is it a DC measurement or is it?
Yeah.
But how does it make
It
contact?
uses capacitive coupling to measure the fields. I don't know exactly sure how that works, but.
But you've got to need the.
But how does it go into them?
Practicalities. More depth information, maybe.
Of the operational aspects.
Yeah, operational aspects.
Yeah, it's easier to do this instruments that you don't.
No. OMAP is a lot easier.
No.
Yeah, it's much heavier, so these are operational.
Well, that's not a problem.
You're not carrying it.
For a surveyor it is, so.
It's enough.
Are those fixed length? They're 10-meter
Yeah.
long surveys? Can you make
I'm
them
not
bigger?
sure. I'm not sure. you should look it up, but I don't know.
But you really want to, or you're applying just to put stakes in everywhere, just leave them, right? You don't want to be repopulating.
Yeah, that would be the nicest option, but we have a problem with the mowing the field. So every half year or every spring they start mowing. So we cannot leave the pins in. Well, we can leave them in for a test for a month or so. Yeah, in that sense, it's yeah, we could have a system which we could permanently leave in.
Yes, very good.
Yeah.
Really good.
Load the soil.
Yeah, but then that is, but then you have to how to connect them then. You have to leave the service line also.
Run it through also.
Yeah.
PVC pipe below the surface, run the cables through. Then they can bounce machine level.
Yeah, yeah, that could, but yeah,
it's a lot of mucking around.
It's also quite expensive still. Yeah, but yeah.
Make some small stuff.
And won't that
yes, there are restrictions, of course, in rummaging around with your isolation, with your caps.
It's 3 meters of clay.
Yeah.
It's amazing with 3 meters of clay that the rain will penetrate into the landfill. Isn't the clay
it's not completely clay. I think I'm not. Yeah, completely sure what precise the content is of the material, but it's. I think it's just earth.
It's
clay. Yeah, yeah, it is. You see the data usually nice when you have a rain event, big rain event, and a couple of days later you have a lot of leachate discharge.
Okay. Interesting. Didn't know things like this happened to the Netherlands. Even living there.
Yeah.
It's all in the background. It's kind of stuff.
Yeah, that's right.
Yeah, just trying to clean up
for citizens.
Yeah.
And you said those are pretty common. Like we've got quite a few of these landfills.
Yeah, we're gonna do this on 4 pilots, but the whole project is connected to, I think, a couple of 20 or 30. Even more landfills through the whole Netherlands, which have more or less the same system. Which, if it's successful, if the treatment is successful here, we can. The idea is to apply it everywhere.
What was the horizontal scale of this?
The
horizontal footprint at the top. How large are
the areas?
Yeah, well, yeah, the pilot area is 2.5 hectares, but that's only a part. So I think the total landfill is around 6 or 7 hectares. But I don't know exactly. Yeah.
What's that translated to?
Oh.
So that would be 200 by 200 meters, I guess.
Yeah, it's quite big. Yeah.
Something like that. 200 by 300 meters. Where are the pilots?
In Almere, there's one, and in Middenmeer, or in the Wierenmeer, up in the north, and there's one in Bergen op Zoom. Nice. Any other thoughts about what type of measurements would be good to, especially measure the water content, or combination of measurements?
The water content, you have this NMR or what is it?
Yeah.
NMR kind of thing in the non-saturated zone.
Mm-hmm.
Yeah, that shows you, gives an indication of permeability, the medium also.
NMR, which that is
nuclear magnetic resonance.
Yes.
Does it? Yeah, I know it in the laboratory.
Protons, and they get flipped and then they spin and they let up.
Yeah, no, I know the principle. I know you have these big reactors in the laboratory, but I don't know how you do it.
They do it in the oil industry for. It costs a lot of money. One tool, $1.5 million. But I'm sure they have it for.
But the Danes, they do it also concerts
Yeah.
on the service. They have a service NMR system.
Yeah.
So you could.
I know it to
Contact them and
identify
So see how
and it's a
expensive it
fluid
is.
type.
Not so.
You can determine if you've got oil or water, depending on the relaxation time. And you can get kind of a milli-Darcy figure out of it.
Okay.
It's very useful for the oil industry, you can imagine.
It's used quite a bit in groundwater.
In soil science.
Yeah, I think these guys are the
there's
ones
other
who-
type of-
Yeah, well,
Oh, sorry.
anyway, thank you for your
Okay.
input as well.
And,
If you do have a paper or two about the background of this, that would be really interesting.
Yeah, there are also some reports, also some paper. I can send it to you.
Yeah, definitely. In fact, there's so many of them, and, there's some really interesting problems.
Yeah, and we're just setting up the industry, so we're also very open to collaboration, or if other groups want to also use it as a test site.
What?
They are here for an hour, so
Well, that's perfect. Thanks very much.
Maybe before we all we were planning to go to invite for a dinner tonight. For those who are interested. So on behalf of the partner, we were planning to go to